and for CSIR Net. Equally applicable. Okay, so let's begin by studying the spherical and cylindrical polar coordinates. I'm not going to bore you with entire how what is spherical, what is cylindrical, but let's begin and let's see some of the very important things in both the coordinate systems. In electrostatics, in electricity and magnetism, people find that it is a very hard subject, and the reason is only one, and that reason is that we do not know how to use spherical and cylindrical coordinate system. Once you know how to use these coordinate systems, the entire electromagnetism will become easy. So what we will do today is very brief introduction about both coordinate systems and then applying these coordinate systems to the problems of electrostatics. Perfect. So one is spherical and one is cylindrical. In Cartesian coordinate system, we know we have, if any point in the space, three-dimensional space, we need 3 points. One is X, one is Y, and one is Z. It is in Cartesian coordinates. So what do we need in spherical if we want to specify any points? We have 3 coordinates. One is R, one is theta, and one is phi. In cylindrical, we also need 3 points. One is S. Sometimes we also call it rho. Here we will call it S. Second is phi, and third is Z. So what are these 3 things? Let's see with the help of an diagram. So here there is a point in the space and O is the origin. So I want you to see on the left diagram of the sphere. So O is an origin. We know first we define a Cartesian or we define an origin. Then we have a point P in the space. How we will define this point? One is R. What is R? R is a distance from this origin to this point P. This is called R. And if we imagine a sphere, imaginary sphere, then the radius of this sphere will be R. And point P will be on the surface of the sphere. Okay, we do not have sphere before. We have the point P. We connect our origin O to point P with the distance R. And now we imagine a sphere of radius R and our point P is on the surface of the sphere. Now the second problem comes that our point can be on anywhere. Here you can see on the lower diagram, I am drawing some points, black pen. It can be anywhere. No? All these points are on the surface of the space. So how do we define where our point is? So second thing we need is how much our point is below this. Does our point is here, 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 here? What is an angle our point is making with the z-axis? So this is our z-axis, this is our z-axis, and this is our r vector. This is our angle theta. Now our point can be here, here, here. So depending on that, our theta will be this or this. So whatever can be our theta. So this is what we call it as longitude. This is what we call it as latitude. Okay, latitude. Theta is called latitude. We know that what is latitude. Either our point is on this line, this line, this line, this line, or this line. At all these lines, your angle will be theta. Okay, at this entire line, our angle will be theta. Our point can be anywhere on this line. And if you draw this line, this will be theta. If you do theta, theta, theta. Okay. This is called the line of latitude. The second thing comes, once you know that your point on is in where on this line, then you need to know that where exactly on this line is your point. Then comes the line phi. This is called phi. So either you are talking about this line, this line, this line, this line, you have to define the angle phi. Have to define the angle phi. In very analytical situations, what we say is the line connecting the point P from origin is called R vector. if you take the projection of this r vector on xy plane, and then the angle which it makes with the x-axis is called phi. Okay, very simple concept, very simple. If you do not understand right now, don't worry, when we will do the problems that will become more clear to you. The second thing we need to discuss here is cylindrical polar coordinates. In cylinder, what happens is, number one, you have origin, this is your origin O, you have this point. So first thing we need to know is what is the distance between, what is a perpendicular distance between this point and the origin. This is called S. So let's say you have a cylinder. Your point can be here, your point can be here, so your point can be here, your point can be here, your point can be here. So from the axis of the cylinder, what is the distance of your point? That is called S, or we can also say radius of our cylinder. That is number one coordinate. Second coordinate is, now as you can be anywhere on the surface, so you need to tell me at what angle you are. So if you define phi, at what angle you are, this is phi, then also second thing is fixed. Now third thing, only thing left is either you are at middle of the cylinder, top of the cylinder, where. So for that you need Z. So these three things you need, S, phi and Z, to define the point in the cylindrical coordinate system, and in sphere you need r, theta and phi. Okay, r is a distance from origin, theta is angle the r vector makes with z axis, and phi the angle which the projection of the r vector makes with the x axis. Okay, we can also define it in terms of latitude and longitude. Now S is a distance of point from the axis of the cylinder. Phi is the angle which this line is making. Okay, if you imagine this, so this is S, and what is an angle this S is making? Okay, so this is phi. Angle can be anything depending on where your line is. And Z is the, you know, Z is, what is Z? How much it is out of the plane. Okay, how much? Here, where it is. So with the knowledge of these two things, now we come to formula kind of thing. And this is very important formulas. These are not very important, but the formulas which you, so I am not explaining why these formulas are here. You can go to any textbook and see the relation of Cartesian coordinate system with the cylindrical and spherical. These are not at all important to solve the problems of electrostatics. But if the question comes directly from spherical or cylindrical, these are important. But the important thing which no books cover is that which I am going to tell you. Now you need to remember along with me some three things only. If you know these three things, you will never forget the formulas of the spherical and cylindrical coordinate system. This is called H elements. No book explains in terms of H elements. Okay. There are three H elements in spherical polar coordinates. H11, it is 1. H22 is R, and H33 is R sine theta. Don't ask me why and what is this H elements. Don't ask me. Otherwise you have to go to tensors. You have to understand entire tensors. So open your book and just remember these three things. In spherical polar coordinates, first H element is 1, second H element is R, and third H element is R sine theta. If you remember this much, problem is solved. Now, in electrostatics, you usually need line elements and area elements. What is line elements? What if your R is changing? Okay, if your X is changing in Cartesian coordinate, you write dx. If your Y is changing, you write dy. And if your Z is changing, you write dz. What if your R is changing? What is the length distance? So that is dr, or you can say h11 multiplied by dr. What is h11? That is 1. So it is only dr. Okay. What if your theta is changing? So can I write just d theta? No, because d theta is not a dimension of length. This does not tells you what is a change in length. It tells you what is a change in angle. So you cannot write this. But then what do we write? We write h22 d theta. What is h22? R. So you write r d theta. And what if phi is changing? You write h33 d phi. And what is that? R sine theta d phi. So your line elements are ready. So what will be, since these are vectors, we need to make them vector. So r vector, theta cap, r cap, theta cap, and phi cap. So this is done. Then comes area element. What are area elements? The small change in small area patch. Okay, if I say in xy plane, what is small area? You say dx dy. If I say what is small area in yz plane, you say dy dz. Okay, so what is this xy plane? XY plane is a plane in which Z is fixed. Z do not change. So similarly, what is DAR? DAR is a plane in which R is fixed. R do not change. So what is change then? D theta D phi. So what we write? H11 D theta D phi into R cap. Whatever is fixed, we write it as R cap. Why? Let's say this is XY plane. So you write this plane by small area by dx dy z cap. Okay, this is it. So whatever is fixed, that is, r cap will come here. So DAR is a small area when the r is fixed, and d theta d phi is changing. So we are writing d theta d phi and multiply by h11. So what is h11? That is 1. So simply it will be d theta d phi r cap. Here now comes h22.
भैया H11 से नहीं होगा.
Oh, sorry. You are right. You are right. You are right. I'm sorry. So what you need to do is, yeah, you are right. So what you need to do is, you need to write, if your R is fixed, then you have to write h22 h33 d theta d phi r cap. So it means if your R is fixed, then the element corresponding to R, which is h11, you do not write that and write other 2h. So what it will become then? It will become r square sine theta d theta d phi r cap. Is it fine now? Yeah. Okay, perfect. Okay, so now comes to dA theta. So what is the meaning of dA theta? I am giving you two options. One is theta is fixed. Okay. What is a small area when theta is fixed? So h11, h33. Now we will not write h22. Okay, h33 d r d phi, and what will be here? Theta cap. So please tell me what will be this. So just do a very simple thing. Just put the values and tell me what will be this.
R square sine theta dr d phi theta cap.
R square sine theta. Are you sure? H11 is 1. H33 is?
R sine theta dr d phi theta cap.
Yeah. Yes, R sine theta dr d phi theta cap. So now entirely, I am not helping you at all. Entirely make the dA phi. Means the small area when your phi is fixed. So first tell me general form. What I need to write here. H, which I need to multiply?
H11, H22,
H22 and dr d theta, and what will be fixed? Phi cap. So this will become r dr d theta phi cap. Okay, very nice. Now coming to the cylindrical polar coordinate system. What are the h? If you know the h elements, you can make the entire line elements, area elements by yourself. Only thing you need to remember is h elements. Also you need to remember is h11 corresponds to r theta and this corresponds to phi. You do not change the order. If you write phi first and theta then you will be in problem. So remember h11 corresponds to r, h22 corresponds to theta and h33 corresponds to phi. This you also need to remember. Okay. So in cylindrical polar coordinates h11 is again 1, h22 is again r and h33 is again 1. That's it, simple. So what will be DLS? Means the change in length when you change in the direction of S cap. It means when you go away from the axis. When you go away from the axis. So what will be that? H11 ds into S cap. So that will be ds into S cap. So tell me what should I write here? DL phi.
RD psi cap.
RD
Psi cap.
psi cap. Okay, perfect. And here I should write dz into z cap. Perfect. Done. Okay, now coming to next thing. What should I write on the first I will do for you? That will be h22 h33 d phi dz into s cap. So this will be r d phi dz into s cap. So what will be here now? Second element. Jaldi, jaldi, jaldi. You have 5 seconds.
Theta d phi.
D phi.
DS.
Okay, ds.
DS. DZ.
Yes. Phi cap.
Phi cap.
Perfect. So girls are more active. Okay, girls are understanding better. Okay, so now any boy, I want to any boy to answer this. Okay, so what is DA phi? Sorry. Here will be DAZ. What will be DAZ?
S ds d phi z cap.
S ds d phi z cap. Okay, perfect. So the last thing which comes here is, so I will just remove it here so I can write it. Volume element. What is volume element? Small volume. Small volume means all three are changing. R is changing, phi is changing, and theta is changing. So how do you write small volume? You just multiply all three. Sorry, d theta, d phi. So it will be r square sine theta, dr d theta d phi. And similarly on here, what will be the value? You tell me. For cylindrical, what will be small volume element?
S ds d phi
R.
d phi.
S ds d phi dz.
Sir,
So
it's R.
no r, we are defining it as in cylindrical. Okay, why we are defining it as a not r? That is a question. Understand this very nicely. If you have an origin, okay, r and this point, and you do not know this is origin, this is point P, and you do not know that either to use spherical or cylindrical, then what will be r and what will be s? R will be the direct distance from this point O to R P. But what will be s? S will be the, first you need to define your z axis, and then s will be the distance from that axis. So this is a difference between S and R, which everybody should remember. I made a very big mistake in the exam by confusing it with S and R. Okay, that is why I'm making it very clear from very beginning. S is a perpendicular distance from the axis and R is a perpendicular distance from the origin. Okay, so that is which you need to remember. So with this information, okay, so let's go to the end of that so that I can explain you what is Gauss law very briefly. So then we can immediately come to our application part, application of these coordinate systems. Gauss's law, very beautiful law in electrostatics. And what is happening in last few years in JAM exam is one question for Gauss law is fixed and the question is becoming harder and harder. In TIFR one, almost one question in Gauss law is fixed. In JEST also almost one question in Gauss law is fixed. In CSIR Net, sometimes direct question from Gauss law comes, or most of the times you have to apply Gauss law in many questions in order to solve your question. So Gauss law is the first step and then there is one more step to answer the question. Okay, so Gauss law becomes extremely important and everybody knows its statement, but no one knows how to implement it. So let's understand. So first I will write one equation and you need to tell me if I have written this right or wrong. So do you think this is a correct form of Gauss law?
Closed integral.
Yes. So this is an important factor. Always remember this is closed. And what is this left hand side thing means? What is E dot ds closed area integral? What does this means? There is a very good word in electrostatics for this.
Flux.
Yes, this is called electric flux through a closed surface. So how much of the electric field is passing through any closed surface? So let's say you have a closed surface. Okay. This is your closed surface. And what is a net electric field passing through it? Okay. So now I have a good question for you. If I have a charge Q outside it, according to Gauss law, the net electric flux passing through it should be zero. And why it should be zero? Let's imagine that. See, the flux, this Q has a flux line like this, means electric field line like this. It will enter from one side and it will leave the other side. So net electric flux coming in is equals to net electric flux going out. So no net electric flux is coming out or going inside the box. So this picture made it very clear that net electric flux coming out of the surface or closed surface or going in the closed surface will only depend upon the charge that is inside that. So that is why we write Q enclosed. What is enclosed? Q enclosed, the charge which is present inside this divided by epsilon naught. So currently we are dealing with free space. We have not introduced any kind of material, so epsilon naught will work very fine. But now let's assume that I put this charge inside this. So this charge will have this kind of electric fields. So some electric field lines are coming out. It means this box will have net electric fields coming out. And if this is negative charge, then electric field lines will go in. So electric field is going inside. So it is a very elegant law, this which describes the physics, that electric flux coming out or going in and closed surface is equal to charge enclosed within that surface divided by epsilon naught. But this statement is not going to help us in the exams. We need to understand how this works in the problem. So the first question I have for you is, there is a sphere. There are two concentric spheres. Concentric spheres means having the same origin. Okay. Inner sphere has a radius A, outer sphere has a radius B. Okay. And there is no charge density, means no charge is present in this area. In this area. Okay. No charge is present outside this area. Only the charge density is present between these two spheres. Okay, I have seen most of the people doing this question wrong, and these kind of question have came in many exams. So now the question is find the electric field in all three areas. This means outside, between, and inside this. How we will do that? Now charge density is also not very simple. It is not the constant charge density rho. It is the charge density which depends upon the distance from the origin. It means the charge density is more here, oh sorry, less here and more here and even more here, because it depends upon R linearly. So as you increase the R, your charge density is increasing, and here charge density becomes 0 because outside there is no charge density. So if I have to draw picture pictorially, the charge density will look like something like this. Okay, so there is a positive charge close to the sphere, it is far away from each other, so density is less. As you move away, the charges are still here but they are closer, it means the density is more. So this is how you imagine the problems. Always remember in Gauss law and in Ampere's law. So please write a statement on your notebook. Okay, I will also write it with you. Gauss law and Ampere's law. Ampere's law we use in magnetostatics, but you write also here Ampere's law. We try to figure out about the direction of electric field, slash magnetic field before solving problem. So if you want to solve the problem, you need to first understand what is the direction of the electric field and magnetic. Only then you can proceed. Okay, Gauss law never tells you about the direction of electric field or magnetic field. Always remember this. So if I have charges like this, you know, for any positive charge, the electric field will be like this, radially outwards. So similarly here also my electric field will be kind of radially outwards. Okay, so I have predicted about the direction before, and what is the direction I have predicted? Radially. Now from here problem starts to work. We do not know the words radially, or we are not familiar with spherical polar coordinates. Radially means R cap. Now we are not talking about X cap, Y cap, Z cap. We are only talk about R cap, theta cap and phi cap. So radially outward means R cap. Perfect. This much if we know. Now we move to second step. Second step is once you know the direction of electric field, then you decide that what should be the Gaussian surface. What is Gaussian surface? It is an imaginary surface that we draw to solve the problems. So let's move to our spherical polar coordinates. So if we are talking about surface, then we have to discuss about area elements. Now tell me, out of these three area elements, which area element should I choose? First one. Why? Because it is also along R cap. Okay, it is also long. Why we need R cap? See, E dot dA. This is your left hand side of your Gauss law. So if your electric field is along R cap, then your small area element should also be along R cap. Otherwise, their dot product will not be non-zero. Their dot product will be 0. So we need a surface in which a radius is fixed, in which R is fixed. So let's draw such kind of surface. Okay, so first we want to know the electric field inside this area. So R is fixed. So I want to know the electric field at this point. This is my origin, and then this point I want to know the electric. What I will do? I will make a Gaussian sphere. So in sphere, you know, if you plot a sphere on this entire sphere, your r is fixed, but is a value of r here, it is a value of r here, r here, but your theta is not fixed, your phi is not fixed, but your r is fixed. So here we do not need to do the calculation. Why? Because tell me what is a charge enclosed within this Gaussian surface. It is 0. So case 1, r is less than a. Okay, so charge enclosed is 0. So your E dot ds is 0 or E dot dA is 0. This simply means your electric field is definitely 0. Okay, now case 2. Case 2 is the most important thing, and this is a case for which we have I have actually introduced you the spherical polar coordinates. Your r is in between. Now we have to find the electric field at this point. So what we do, we draw a Gaussian sphere in such a way that this point comes on the surface of the sphere. Now the question comes, first we need to solve LHS, left hand side. E dot dA. So let me write dA here. dA is r square sine theta, d theta d phi r cap. Okay, so this will be equals to E dA double integral E r square sine theta d theta d phi. Okay, and now since we can keep electric field outside, why? Because our electric field only depends upon the distance from the center. Our electric field is a function of r only. Okay, our electric field is not a function of theta or phi. And what is changing here? Theta and phi. So we can bring this E outside integral. We can bring r square outside because r is fixed also. So sine theta d theta, and we just separated these integrals phi. So anybody, now you have a basic understanding of BSc. What is the limit of theta? Theta changes from 0 to pi. Everybody knows. And phi changes from 0 to 2 pi. So if you solve this, you will get 2. And if you solve this, you will get 2 pi. So what you will get? E into 4 pi r square. So now you understood. In questions, you are directly going, you use E into 4 pi r square. The area of this sphere is 4 pi r square. So you just used to multiply it. So now you understood how this actually used to come 4 pi r square. But this is not our main idea. Left hand side is easy. Right hand side is a big problem for us. Now let's do right hand side. Okay, so what is charge enclosed? So I first want you to see this image again. This image. Your charge density is not here. Your charge density starts from here and till here you have to see how much of the charge is enclosed. Okay, within this area, but how much of the charge is enclosed. So how we will do that actually? You know, am I right? Charge enclosed is density multiplied by, am I right or wrong? I know you. Batao. Density is a charge upon volume. Okay, charge upon volume. So this is right, na? Density into small volume, or let's do like this. Small charge enclosed in a small volume is rho d tau. What is the total charge enclosed? Rho d tau. Okay, so that is I have done correctly. Now understand very clearly. If your charge density was constant like this, so then you can simply find charge enclosed equals to rho naught into V. That is a total volume. But here charge density is not constant. Here charge density is not constant. That is why I am using this formula. If your charge density was constant, what you do is simply multiply charge density with the volume. So let's do this one first, so that if any other question comes, you can also do that. So what is the volume of this sphere? Sorry. What is the volume of this Gaussian sphere? We want to know what is charge enclosed within this. Volume will be 4 by 3 pi r cube. But here is a trick. Your charge density is not available everywhere inside this volume. It is not present in this inner volume. So you have to subtract the volume of inner sphere, that is 4 by 3 pi a cube. So in this our situation, when charge density is constant, our answer will be 4 by 3 pi r cube minus a cube. This is your charge enclosed, but now our charge density is not constant. So till here, do you understand how I did this? Anybody who do not understand, I will explain it again.
Understood there.
So it is very quite simple. If your charge density is simple, charge enclosed will be constant density multiplied by volume, and volume is this entire volume minus the volume in which charge density is not present. Simple. But now we cannot do this in this situation. Why? Because rho is not constant. So how we then solve it? So now I will not go up and tell me what is a volume element in spherical polar coordinate.
R square sin theta dr d theta d phi.
Perfect. R square sin theta dr d theta d phi. So what will be Q enclosed? Three integrals. What is your rho? Rho is kr. Rho is kr. It is given in the problem. So we put the value of kr. Then we put r square sin theta dr d theta d phi. Let me reduce the size of the pen. I'm not able to do the good handwriting. Okay. So now k is constant. K can come outside. You can write r cube dr sin theta d theta and d phi. So now the question, very important question, and I only want girls, any girl to answer this question who haven't answered before. What will be the limit of r? Limits of r. I want you to see this problem, see this diagram very carefully and tell me what will be the limits of r.
A to B.
No, a to r. Okay, we are talking about till here only. So this is at distance r from here, and we are starting from this point. Okay, if I remove this, so we are talking till here, till r, and we are starting from a, because inside this charge density is not there. So my limits are a to r. Now theta has same limit 0 to pi, and phi has same limit 0 to 2 pi. Okay, so if I solve this, I will get k by 4 r raised to power 4 minus a raised to power 4, and these two will get 4 pi. So what I will get? Pi k r raised to power 4 minus a raised to power 4. R cube, perfect. So now I just need to put LHS equals to RHS, and I will get, this is my LHS. So E into 4 pi r square. Did we made any mistake or is it okay? Okay. Pi k r raised per 4 minus a raised per 4. I have a very good question coming up for you. You are going to be actually, you are going to beat me now. Okay, r raised per 4 minus a raised per 4. 4 epsilon naught r square. This is an electric field between the 2 points, means 2 spheres. And if anyone tells you write in terms of vector form, then just make a vector and on right hand side put r cap, because before starting the problem we said that the electric field is going to be towards r cap. Now the question for you is, let's say you have a point charge, then your electric field varies as 1 by r square. है ना? Am I right or wrong? Your electric field varies as 1 by r square.
Yeah, 1 by r square.
But now here, see here, your numerator is r raised per 4 and your denominator is r raised per 2, r2. So your electric field is varying r square. So how can this happen? How can this happen? We should get this. We should not get this. This is wrong. But this answer is also right. This answer is absolutely right. Then what is the problem? आया मजा? ऐसे होता है इंटरव्यू में. कनेक्शंस बनाना. हाँ बताओ.
एक जीरो पर आर स्क्वायर के प्रोपोर्शनली आएगा.
बिल्कुल नहीं. क्या कह रहे हो तुम? दोबारा बोलना एक बार.
ए जीरो हो जाएगा तो कैंसिल आउट हो गया. आर पर 4 बाय आर स्क्वायर तो प्रोपोर्शनल का आर स्क्वायर क्या है?
हाँ, प्रोपोर्शनल टू आर स्क्वायर आ रहा है, लेकिन प्रोपोर्शनल टू इनवर्सली आर स्क्वायर आना चाहिए. दिस इज व्हाट आई एम आस्किंग. If I make a 0, or if you don't have to make a 0, it is just a constant. So if you do that, so your E becomes, so let me give you an answer without wasting a time. So should I give the answer or anyone is thinking?
Bhaiya,
Huh.
since charge density is increasing as we go along R, I think electric field is increasing as R square.
No, electric field is also okay. Electric field also have to
increase, right? Because charge density is increasing, no, as we go away from R, radial outward from R.
Yes, because we are talking about inside this, है ना? Inside this area. Inside this area, as you are moving away from the origin, your charge density is increasing. So your electric field should not actually decrease, it should actually increase. The person has answered correctly. Okay, everybody understood? Usually what happens is, if we have a charge and if we go very away from it, this our electric field decrease by amount 1 by r square. But here, as you are moving away from origin, your charge density is increasing. So if charge density is increasing, then your electric field must increase by r square. Okay, that is a very good. Okay, now coming to next further thing. Last portion which is left is outside the outside. So r is greater than a. So only thing which we need is charge enclosed. Now charge enclosed we have already find out here. Okay, charge enclosed is already find out here. So the only thing which we need to do is, so let's write it here first. R cube dr sine theta d theta and d phi. So only thing which we need is just change the limits. So now the limits are from a to so let me again tell you about the surface. Now you are want to find electric field here. So this is a Gaussian sphere. But your your charge is only from A to B. Okay. So your charge is only from A to B. So you won't write R here. Why? Because till R you don't have charge. You have charge only till B. Okay, so this will become 4 pi k by 4 b raised per 4 minus a raised per 4. Okay, and your left hand side is already we know E into 4 pi r square, and this is pi by epsilon naught b raised per 4 minus a raised per 4, and your electric field will be b raised per, sorry, here will be k also, k. So k, so k b raised per 4 minus a raised per 4 into pi epsilon naught r square. So now you can see your electric field is varying as r square, or is it still varying as r directly proportional to r square? Which one is this now? A or B?
B.
B. Why? Because b raised per 4 minus a, b raised per 4 minus a raised per 4 is constant. It is constant because b is constant, a is constant. Okay, only thing r is in, E is inversely proportional to r square. In previous case, upper part was not constant, it was r raised per 4 minus a raised per 4. Okay, that is why we had this thing, but here it is okay. Here we have this. So let's try to plot this. Let's try to plot this. So this is our electric field and this is our R. So let's divide it 0 to A, 0 to B, and then forward. So what is an electric field till A?
0, sir.
0.
0,
So
sir.
let's, yes. So let me increase the pen size and change the color. So 0 A, it is 0. Now it increases by amount R square. Okay. R square, and then it starts to decrease by, everybody understood how we plotted this? E directly proportional to R square, E inversely proportional to R square.
Yes, bhai.
Absolutely great. So problem number 1, this was a problem number 1. This was actually not problem, just one problem. I included many problem in it. So do you understand this entire problem? Do you have any doubt at any position? Tell me.
So, bhaiya, this graph also tells that at B that electric field is maximum. Am I correct?
Yes, you are correct. You are absolutely correct. Okay, so no problem. Everybody understood? Yes, no, anything?
Yes, sir.
Perfect. Perfect. So now come to problem number 2 and just solve it in 5-10 minutes and then just wrap it up. So same thing for cylindrical, but now I am making it little easier because we don't have to repeat everything. So it is an entire cylinder. Charge density inside it depends upon S, distance from the axis. So how we plot this? This, like this. And here the charge density becomes very close to each. So this is a kind of charge density we have. This is all entire sphere, so sorry, cylinder. So now we have only two areas, inside cylinder and outside cylinder. Okay, so first thing, first notebook, first line which I wrote in Gauss law, before starting the problem you have to predict how the electric field is. So if you have a line which has a charge like this, so your electric field will like this. It means in the direction axially outward, that is S cap. So everybody can imagine electric field will be like this. That is in the direction of S cap. Now we only talk about three things: S cap, phi cap, Z cap. Okay. Only these three things. Now we are talking about cylindrical coordinate system. So who told us that we should talk about cylindrical? That is because our electric field is diverging out or coming in from an axis. Okay, from an axis, not from a point. In sphere, it diverges out from a point. That means r cap. If it diverges out from a complete axis like this, it means s cap. So this is a difference. That is why we are using cylindrical polar coordinate system here. So let's talk about area number 1. So region number 1, let's draw a imaginary Gaussian cylinder of length L. Gaussian cylinder of length L, and we want to know the electric field at this point. So S will be and radius S. Okay. So what will be the charge enclosed in this? Again, the same thing. Rho d tau. So because rho is not constant. So what is d tau in cylindrical? It is S ds d phi dz. Our rho is ks. Our d rho is ds d phi dz. 3 integrals. Let's separate out these integrals. K can come out. K can come out. What is rho here? Not rho, sorry, S. Sorry, S. S square ds d phi and dz. So first tell me what is the limits of S. You want to talk about this point. You are starting from this point. So your limit of S is 0 to?
Yes.
Yes. सबको समझ आया ये? 0 to S, or is there any problem? What is S? S is, huh? Batao?
No problem, भैया.
Okay, perfect. So what is the limit of phi? 0 to 2 pi. And what is the limit of Z? 0 to?
L.
L. The length
L.
of our, yes, the length of our Gaussian sphere. So this will be 2 pi, this will be L, and this will be S cube by 3. So 2 pi KL by 3 into S cube. So have I done it right? Okay. So now what is on left hand side? E dot ds. Or dA we should write. Okay. To avoid any confusion. So what kind of A is this? This is an A in which S is constant because we need S cap. So H22, H33. H22 is S, H33 is 1. S d phi dz. Okay, this is our, so E S d phi dz double integral. E we can bring out, S we can bring out, d phi dz will be 2 pi into L. You can easily do this calculation. 2 pi L into E into S. So now just equate both things. What is charge enclosed? This is our charge enclosed. So let's copy it and let's paste it here. So 2 pi cancelled. L is also cancelled. So our electric field is Ks square by 3. So there will be epsilon naught also. 3 epsilon naught. So have I done all the steps right? Everybody satisfied?
Yes, sure.
Okay.
Yes.
So then case 2. when our S is greater than A. What is A? A is a radius of the cylinder. Okay. So again, charge enclosed we already have. This is our charge enclosed. Only thing which we need to change here is limits. K S square ds. So now the limits will be from, batao, what will be the limits of S?
0 to A.
0 to A. Why A? Because our charge exists only till A. Outside that our charge do not exist. So what will be now answer? 2 pi k L A cube by 3. And now we can again repeat the same step. 2 pi LES equals to 2 pi k L A cube by 3 epsilon naught. And what will be our electric field then? 2 pi L cancels. Okay. K A cube by 3 epsilon naught S. So see the difference. Inside cylinder electric field increases as S square. Outside the cylinder E decreases as S. So the same thing which we will do again. Let's plot it. So how do you plot it? This is S, this is E, this is your red marker, this is up to A. Up to A, your electric field increases as S. Square, sorry, it increases by S square or S? S square. So your electric field is increases S square. And decreases by S. So decrease will be little slower. Okay, because it is decreasing by S, but increases by S square. So increase is fast, decrease is slow. And this is your point A. So these were the two problems. If you understood these two problems, I don't think so there is any problem in electrostatics which you cannot do. Because now you understand how to apply the spherical and cylindrical polar coordinate system. And I can easily bet you cannot find it in any book or any video. Okay. If you do find, send me that. Any problems in today's lecture? I think I will end up here. So everybody understood what we did today?
Yes, sir.
Yes, भैया.
Okay. That is, I am glad. Okay. So, okay. So people who need assignment, okay, please raise your hand. Only 3 people need it. Okay, many people. Oh, sorry, immediately many people. Okay. Okay, so let me just show you an assignment. Okay. So let me share you a screen. Let me share my screen. Sorry, and okay, just a second. So can you see the screen? No, I don't think so. You will be able to see the screen right now. Let me do it again. Can you see the screen now? On the
Yes,
laptop?
भैया.
Yes.
Yes,
So
sir.
now, yeah, yes. Huh? Okay. So you all can see the screen. So in this is a, I have arranged the means one of my intern, the people I have hired for internship. So this person has done a very good job and arranged the questions of electrostatics, means entire electromagnetism of CSIR Net exam topic wise. So this is electrostatics, this is special topics of electrostatics, all these questions. So I will share this PDF. Okay, I will share this PDF in the group, and you need to solve the question number second. Please mark it down. So I will also mark it down. Question number second, which is directly related to the questions which we have discussed today. Question number second, question number fourth, okay, question number sixth, question number seventh, question number eighth, question number 10, okay, and question number 17, okay. So these are the questions. So anybody repeat the question which I have said? Question number second.
Question number second, question number 4, question number 6, 7, 8, 10, and 17.
Perfect. So if you practice all these questions from this, okay, so I will only share this PDF in which there are questions. I will not share the PDF in which there are solutions. That is actually available to the course students. So this PDF I can share. There is no problem. I think this will help you. So this PDF I will share. Okay. And these questions you need to practice, and not just practice, send the detailed solution and your option very clearly in the common group. So once you solve the question, send its picture to the group. Okay. And let's see how many of you are actually doing. So if more of you will be doing, these classes will run for a long time. If less, or if the people will get listening, I will not continue it for very long. Okay. So best of luck. Do these questions. And with today's lecture, I will share the recording by tomorrow. Either it will be in group or it will be on YouTube, depending on what is the quality. I will check the quality. Okay. So goodbye, everyone. I hope you learned today. If anyone has questions, okay, you can ask. Okay. Bye bye.
Thank you, Bhaiya.
Okay. You're welcome.
Thank you, Priya.
You're welcome. You're welcome.
Thank you, sir.